Hello and welcome. Today we're jumping into a huge topic in calculus, integration. But hey, don't let that big word scare you. We're going to look at it as simply the reverse of something you might already be familiar with, differentiation. Let's see how looking at things backward can actually move our understanding forward.
So let me ask you this. Think about being in a car. Your speedometer tells you your speed at any given moment, right? That's a rate of change. But what about the total distance you traveled? Well, answering that exact question is precisely what integration was designed to do. It's the tool that lets us rewind from a rate of change to figure out the original quantity.
So here's our game plan for today. We'll kick things off by flipping differentiation on its head. Then, we'll get a bit more formal and meet something called the antiderivative. After that, we'll build up our toolkit. I'll show you some common traps to avoid, and then we'll put it all together to solve a real-world problem.
All right, let's dive right into that first section, calculus in reverse. At its heart, this is a really simple idea. It's all about undoing the process of differentiation to get from a rate of change all the way back to the original function.
This comparison really lays it all out. Think of it like this. Differentiation is like glancing at your speedometer to find your speed at one specific instant. Integration, on the other hand, is like using all of those speed readings from your entire trip to figure out the total distance you traveled. One breaks the journey down, the other builds it back up.
So this whole idea of building back up needs a proper name, right? In the world of math, we call this finding the antiderivative. And that introduces us to the idea of the indefinite integral.
Okay, don't let the symbols freak you out. That long stretched out S symbol and the dx at the end, just think of them as bookends. They frame a function and are basically just asking a question. What original function, if you differentiated it, would give you this thing we see right here?
So let's try it out. If we know the derivative, the rate of change, is 2x, what was the original function we started with? Now, the first thing that probably pops into your head is x squared. And you're not wrong. But is that the whole story?
And this is where things get really interesting. The derivative of x squared is 2x, for sure. But take a look at x squared plus 3. Its derivative is also 2x. Why? Because the derivative of any constant is just 0. It vanishes. The same thing is true for x squared minus 5, or x squared plus literally any constant you can dream up.
And that, my friends, is why we have the mighty plus c. It's our way of acknowledging that a whole family of functions could be the right answer. It's a placeholder for any constant number that disappeared during differentiation. Forgetting the plus c is probably the #1 mistake people make, so burn this into your brain. Always, always, always add the constant of integration.
Okay, so we've got the big concept down. We understand the antiderivative and the constant of integration. But how do we actually find them without just guessing all the time? Well, that's where our integration toolkit comes in. Let's look at the basic rules.
These rules are going to be your best friends. And you know what? They're basically just the rules for derivatives, but in reverse. Super useful. They let us take a big, messy function and break it down into smaller, bite-sized pieces that are way, way easier to integrate.
And here it is, the MVP of your integration toolkit, the power rule. It's simple, it's powerful, and you're going to use it constantly. All you do is increase the power by 1 and then divide by that new power. Boom. Now, there's just one tiny catch. This rule works for pretty much any number except when n equals -1. That's the special case for integrating 1 over x, which gives you the natural logarithm of x.
All right, so now that we have a few rules in our back pocket, it's just as important to know what not to do. Honestly, understanding the common mistakes is one of the fastest ways to really master integration.
And here's a crucial point. It's really tempting to think that integration rules work exactly like differentiation rules, especially for things like products. But they don't. Let's look at 2 of the biggest traps people fall into.
First up, while you can totally pull a constant number out in front of an integral, you can absolutely never, ever do that with a variable like x. Moving a variable outside fundamentally changes the math and will give you the wrong answer every single time. Don't do it.
This one is huge. With derivatives, we have that nice, neat product rule. With integrals, not so much. You cannot just integrate the first function, integrate the second one, and multiply them together. It just doesn't work. Integrating products requires some more advanced techniques. So, With all these traps, what's your safety net? It's simple, and it's the best habit you can possibly develop. If you're ever unsure about your answer, just differentiate it. If you get back the function you started with, you know you're correct. If not, it's time to go back and check your work.
So, we have the core concept, we've got the rules, and we know the traps to avoid. But why does any of this matter? Let's see how it all comes together by using our new toolkit to solve a real-world problem.
This example brings the whole thing to life. So, step 1, we start with a rate, the stone's velocity. Step 2, we integrate to get a general formula for its height, which includes our good friend plus c. Then, step 3, we use an initial condition, the fact that it started on a 50-meter high tower, to solve for c and pin it down. Step 4, we write out our final specific equation. And with that, we can answer the actual question.
And after we plug in 3 seconds, we find the height is 87.5 meters. And just like that, we've gone from a rate of change, velocity, to a specific tangible value, the height of the stone at a particular moment. Now that's the power of integration.
So, let's pull it all together. We've seen that integration is just anti-differentiation. It's the amazing tool that lets us work backward, from a rate of change to an original amount. And whether we're talking about a company's total profit or the volume of water flowing into a reservoir, this process is everywhere. So I'll leave you with a final thought to chew on. What other real-world quantities are just waiting to be found by adding up tiny changes?